So, um, we are starting off in section 2.2 of the book, which I think is a terrible place to start because at this point we don't even know what a differential equation is. That's kind of lost in the nuances of chapter 1 that I think we're skipping. But I feel like it would benefit us to kind of take a step back and figure out what a differential equation exactly is. So this is a differential equation. We could spot that by seeing that it's some function of y and there's derivatives in it. And at this point, we don't know how to create them ourselves. We just know how to prove or disprove if a solution makes that a differential equation or not. So we're asking to prove if this equation and this equation are solutions to that differential equation. So this is how we go about doing it. If we notice here that this is a second order differential equation because it has y double prime, all we have to do is take two derivatives of this and then just do a couple substitutions. Let me show you. So we have y prime of 1 equals 3 e to the 3x. And we have y double prime of 1 equals 9 e to the 3x. That's just basic derivative rules with e's and exponents. I figure you guys know your calculus on derivatives pretty well at this point, so I'm not going to bother with the specialties of that. So at this point, all we have to do is substitute. We see that it's claiming that y double prime equals 9 of y. We have y double prime here. So we know the left-hand side is 9e to the 3x is equivalent to 9 times whatever y was. And we're saying y is this. So we see, in fact, that those solutions are true, or that equation is true. It makes it a differential equation. Same song and dance for this one right here. We just take two derivatives of this. Bam. So y prime of 2 equals negative 3 e to the negative 3x. And y double prime of 2 equals 9 e to the negative 3x. Same thing, plug it into our equation in the respective spots for the y double prime and the y function. So we have 9 e to the negative 3x is supposedly equal to 9 times y, and y is just e to negative 3x. And that proves that both of these equations are solutions to that differential equation. And that's pretty much all you're doing. If you remember your calculus 1 derivative rules, chain rule, product rule, these can get quite hairy sometimes, but it's nothing you haven't seen before, so I'm confident you guys could do that. Here's one more quick example. We are given a differential equation, just a first order differential equation. What I mean by that is it only goes to y prime. It's a first order derivative, so it's a first order differential equation. And we're asking to prove if this equation is a solution to that differential equation. So let's try to prove it. So it looks like we only want to go to y prime here. So y prime equals negative 6 e to the negative 2x. Just drag that down and multiply. So now let's do some substitutions because we wanted y prime and we want a regular y here, which we have right here. So negative 6 e to the negative 2x is supposedly equal to 2 times 3 e to the negative 2x equals 0. Did I say it should be equal to? No. Addition here. We're trying to prove that it equals 0. Multiplying that in, we see negative 6 e to the negative 2x plus 6 e to the negative 2x equals 0. We have a negative and positive that cancel out, so 0 equals 0 in effect. So this is a solution to the differential equation. So that's pretty much it as far as proving it. Like I said, you might have to do some quotient rule, might have to do some product rule. There might be some really hairy chain rules with cosines instead of exponents, instead of, who knows what. But this is the general process. Now let's move on to calculus 2 stuff. And by that, let me show you what I mean. Okay, so now we're up to speed with section 2.2 where we are in the book with Will's class. This is the most basic form of a differential equation right here. And I mentioned calculus 2 because before proving that an equation was a solution to a differential equation, all we were using was derivatives. At this point, to create our own equation, we have to use integrals. Let me show you what I mean. We know that a solution to a differential equation, it looks like a function in terms of y equals something. Well, the only y I see there is kind of anchored by this dy dx. So a way that I know I can make this a little more simple is just multiply both sides by this dx. So I could say dy equals x minus 2 squared dx. So essentially what we have is the derivative of y. So we know that we can undo derivatives using integrals. So if I do the integral dy, I'm just going to end up with something y equals, which is exactly what I want. If I want to take an integral of this side, however, I have to take an integral of this side, which is why it now becomes kind of familiar to just some u sub that we would do back in Calc 2. Let me go over here and write this down. I need more room. Woo. So we know this left-hand side, that just turns into y, and that equals some integral x minus 2 squared dx. Well, this is just a u sub. U equals x minus 2. Oop, minus 2. Du equals 1 dx. So we're going to get y equals integral of u squared du. Add 1, divide by the number. So y equals u to the third over 3. And just make our substitution back in. So y equals x minus 2 to the third over 3. Oops. I would have got so marked down. Oh my goodness. Plus c. There we go. And you'll see in the future here why that plus c is so important. Now, it kind of seemed like a gimme back in Calc 2, but here it legitimately is important. So this would be your solution for that differential equation right there. Checking my notes. Yep, go. All right. So let's move on to this one. And again, with the kind of the proving and showing that it's just basically your derivative rules, your product rule, your quotient rule. Same thing here. You're going to use the same methods. You're going to use u sub. You're going to use integration by parts, partial fractions, trig sub. Hopefully not, but you might see it. This isn't anything you haven't seen before. It's just a new process to go by. And feel free to use whatever tricks you need to use to kind of get by this. We're not teaching you to do integrals anymore. We're just teaching you what you can do with them. Actually, this right here is another u sub. So let me write the more spicy problem down. There we go. So we might get something like this. I see right away, okay, same process. I just want to do dy equals 10 x squared plus 1 dx. Take an integral both sides. Now I'm going to pull that 10 out of that integral right there, because I know that this whole equation, 1 over x squared plus 1, is just multiplied by that 10. And it's just some constant multiple we could pull out. And that it might let us see things that we wouldn't necessarily see before. Okay. So like I said, solve these by whatever means you see fit. Like, you don't have to do these by hand anymore. You might remember this from an integration table as being inverse tan. So I'm going to drag this over here. So we have y equals 10 tangent inverse of x plus c. So that is the solution to this differential equation right here. Yeah, that's pretty much it. You will see different variations of this, but hopefully this can get you guys started on the right track. I might make more videos like this, maybe, if, if time permitting. But I will link in the bottom of this video where I'm getting all this information from. He's a professor his name is Leonard, and he is much better at explaining this than I am, and he probably does it in a shorter amount of time too. So I will link down the video. Hopefully this was helpful, guys. Yeah, see you.